India. So this is the presentation outline. In the next around 1 hour, my presentation will focus mainly as it starts with a very brief introduction towards heart sound analysis and its importance, followed by the state of art. Then we will switch over to the problem statements, and there we will find there are many interesting problem statements related to heart sound analysis. And then I will split the recent works which have been done in almost last 5 years into two presentations, today as well as in tomorrow's presentation. We will see the results, the major contribution made in this area, followed by the conclusion. So just to start with, let me start with the basic key word that is called heart sound signals, that is the phonocardiogram signal. So when we talk of phonocardiogram signal, basically it's the heart sound recording. When so it's quite different from ECG signal. So when we talk of phonocardiogram signal, actually it's the it's the recording of heart sounds which is caused due to the mechanical vibration of the heart. And basically in other words we can say that phonocardiogram signal is actually it's the graphical representation of heart sounds. And so this is a phonocardiogram signals. In layman's language it's our heart sound signals, whereas our electrocardiogram signal, uh, this electrocardiogram signal, it refers to recording of electrical activities of the heart. So these two sounds are quite different, though both the sounds carries vital information regarding the health condition of the heart. So when we talk of this phonocardiogram signal, so this phonocardiogram signal, mainly it has some components in it. So when we listen to heart sound signals, even the physician or the cardiologist, when they put the stethoscope to the right area of the chest, and then they listen to the heart sounds, and this process is known as auscultation. So with this process of auscultation, physicians or cardiologists can understand the exact health condition of the heart. And these heart sounds or phonocardiogram signals have different heart sound components in it. Like we say that the first heart sound is S1, second heart sound is termed as S2, third heart sound is S3, and the fourth heart sound is S4. So these are the heart sounds which can be heard, or these are the basic components or the heart components uh, of the phonocardiogram signal. And from this plot or from this table we find that most of the frequencies of these heart sound components or phonocardiogram signals components like S1, S2, S3, and S4, the frequencies are very low here. We say that these signals are of very low frequency. We can see that the frequency range of first heart sound is from 20 hertz to 200 hertz, whereas S2, its frequency is slightly higher, it's 25 to 400 hertz. So likewise, third sound, which is known as S3, its frequency is quite lower, and it becomes very challenging to detect S3 or to hear S3 from the phonocardiogram signal or from the heart sounds. And so mainly this table is presented here to mention that these heart sound signals or the bio origin signal is a very low frequency characteristics, as well as it has low amplitude in nature also. So it's a low amplitude and low frequency signals. And this from this graph we can see, like here we have the signals, like if we see the upper part of this figure one, so this is called phonocardiogram signal, PCG signal. So here we find that here the first sound is your S1, then after some time we see the another heart sound, that is S2. Likewise, so these are also known as lub dub heart sounds. So these are lub dub, lub, dub, lub, dub. So whenever we do auscultation, or when we put the stethoscope on the right area of the chest to hear the heart sounds activities, then we will hear these sounds: S1, S2, S1, S2. These are called lub dub sounds, and these are the fundamental heart sounds. These are the normal heart sounds, and these phonocardiogram signal or PCG signal, or similarly or simply heart sounds, is related with our electrocardiogram signal. So this PCG is the recording of heart sounds caused due to mechanical vibration of the heart, whereas electrocardiogram signal is the recording of electrical activities of the electrical activities of the heart. So here these two are associated, these two are interconnected with each other. We can find that this S1 signal, basically it starts after R peak of the ECG signal, and it's around 10 to 50 millisecond, and the duration of this S1 sounds is also for a very small duration. It occurs uh, approximately on average of 120 milliseconds. Similarly, like when we see this S2 second heart sound signal, so it also starts after R peak of the ECG signal, after the 200, around 280 milliseconds, and it lasts for 80 to 160 milliseconds. So these S1 and S2 sounds are quite normal heart sounds, whereas so this S1 and S2 is present in all the heart sounds, whereas the third heart sound, which is known as S3, so this may be, it may be a normal in case of childrens or juveniles or those who are good athletes, but this may be its presence or its appearance in adult or in elderly people. It may be a sign of cardiac abnormalities. So this S3, it may not be its presence may not be normal in case of some adult people or elderly people. Similarly, S4, the fourth heart sound, this is also a very rare heart sound, and it indicates some cardiac abnormalities in human being. So mainly this slide was mainly prepared to just give a brief introduction to phonocardiogram signal, which is our heart sound signals. And these heart sound signals are a very low amplitude and low frequency signal, and it had different components. It has normal components, which are S1 and S2, first and second heart sounds. This is fundamental heart sounds. It's present. These sounds are present in healthy people, whereas S3 and S4 sounds are the abnormal heart sounds. If there is a presence, or if someone can hear S3 and S4 in adult people or in elderly people, then it indicates some cardiac abnormalities. Similarly, like besides this S3 and S4 heart sounds, we have heart murmurs. So these are some pathological heart murmurs. So these represents some cardiac abnormalities. So just before discussing about why we do heart sound analysis, rather what is the importance of doing this heart sound analysis using signal processing techniques. So before I discuss on this topic, let me just share one small video to know exactly how these heart sounds looks like, or how it sounds, or how one physician hears this heart sounds. So let me uh, let me uh, let me off. I can put my camera off here now for the time
Yes,
being.
yes, you can.
Yeah, yeah, yeah. Just a minute.
But sound will come or not? I don't know. Sound will come or not?
Okay. My mobile is on, so I will just contact you. It will. It should come. Okay.
Okay.
Or just a minute. Uh, okay. Okay. First, let me show the normal heart sounds. So here, like this is the first heart sound S1, and this is the second heart sound S2. So we can hear that it is like S1, S2, S1, S2. So the timing difference between the first heart sound and second heart sound is more as the distance or the time between first heart sound and second heart sound. This is called systolic time, and this time is less as compared to the time difference between the second heart sound to the first heart sound. And we will see S1, S2, then S1, S2, then again S1, then S2. So here the timing between S1 and S2 is low as compared to the time difference between second and third one. So we have S1, S2. S1 is known as lub. S2 is called dub. So lub dub, lub dub, lub dub, lub dub. So it goes on, and these are the healthy heart sounds. And this timing from S1 to S2, which is less, is called systolic time. And the time between the second heart sound to that of the first heart sound is known as diastolic time. So systolic time period is less as compared to the diastolic period. And in case of some of the diseases, this time interval may be get affected. But in for healthy persons, the systolic time period is always less as compared to the diastolic time period. So this was the normal heart sound, and then there is a abnormal heart sound, which is our third heart sound. So so here one can see that that this is your, here in this case this is the first heart sound S1. This is the first heart sound S1, and this is the S2, and the timing between S1 and S2 is less as compared to between S2 and S1. And just after the S2, we have one heart sound that is called S3. So this is the S3 heart sound. You can hear this S3 sound. I hope the sound is very low in amplitude, but hope you can understand these sounds. Okay, let me play once again. So this is the first heart. This is the S1 here. S1. Okay, so these are the actually this is here. This sound is your S3 sound. So this is the abnormal heart sounds. So I have downloaded this thing from thinklabs.com. So it's freely available. So likewise, we have murmur heart sounds, which shows some abnormalities. So we have like innocent murmur, pathological murmurs. So this is one example of a heart murmur. So these heart murmurs, actually, these heart murmurs generally these are present in the first and second heart sounds. In between first and second heart sounds, or in between second and third heart sounds, or from second to first heart sound. So likewise, like if it is lies in S1 and S2, then it is called systolic murmur. But if it lies between S2 and S1, then it will be known as diastolic murmur. So we have different kinds of heart murmurs, which indicates uh, heart abnormalities. So again, let me come to my presentation. So like now the question is like why we go for some heart sound analysis. So actually these heart sounds or the phonocardiogram signal, these are these contains vital information regarding the condition of the health. So if any alteration occurs in heart, if any changes occurs in the physiology of the heart, there it reflects in the heart sounds. So if physicians just identify any alteration or variations from the normal heart sounds, then they understand that there is some abnormalities in the heart, and accordingly they proceed. So importance of heart sound lies in fact that uh, that that these heart sounds contain vital information, important information regarding the condition of the heart of the patient, and any alteration in the normal heart sounds, it indicates cardiac abnormalities. So that's why researchers uh, have uh, have have done the analysis of these heart sounds using various techniques in signal processing and in machine learning. So mainly these tools or this analysis is made mainly to assist physicians in diagnosis heart malfunctions accurately. And as when physician or cardiologist they do auscultation, when they try to hear heart sounds, and they try to understand the cardiac abnormalities. So this process is quite subjective and it requires expertise, and and it varies from person to person. Even a cardiologist can make mistake in hearing the sounds, because these heart sounds are very non-linear signals, and as we now know that these are very these heart sounds are of very low frequency signals and low amplitude signals. That's why even people makes mistakes, and it's quite subjective. For one cardiologist, one person may have maybe normal, but some other cardiologist may say that no, it's an abnormal heart sound. So it's quite subjective, and it requires uh, expertise of the cardiologist. That's why this automated segmentation or analysis of these heart sounds using machine learning techniques or signal processing techniques, it may help us to prevent the mistakes which is caused by the cardiologist and physicians. And definitely this analysis using signal processing, it will improve the quality care for the patients. So the main motivation for doing heart sound analysis using signal processing techniques are mainly it comes from the fact that according to World Health Organization, cardiovascular diseases are the number one cause of death globally, and 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 almost 31.33% of the global health is affected by the cardiovascular diseases. And and the most conventional and easiest method is our auscultation process. So stethoscope is most widely used frontline instrument, and it becomes a symbol of profession also, medical profession also, to detect heart or cardiac abnormalities. But this stethoscope, when it is put on the right part of the chest to hear the heart sounds by the physician or cardiologist, they also make mistakes. According to one of the research and the report submitted by American Cardiac Association, they have told that around 50% of the physician, they do mistakes, and their prescription goes to uh, goes to cardiac hospitals, where at the end people find that that person was quite normal. And this situation leads problem for the patients. And this interpretation of heart sounds by the stethoscope or by the auscultation process, these are quite subjective, and these are the mixture of sounds with complexity. These heart sounds are very complex in nature, and sometimes because of its low amplitude, low frequency, and non-linearity, it becomes very difficult to exactly detect the abnormalities from the normal heart sounds. That's why the main goal of the hard sound analysis using signal processing and machine learning is to create a first level of screening of cardiac pathologies using signal processing technique that may assist the medical experts. So this was uh, mainly to build a background that why we go for hard sound analysis, what is its important, and what should be the goal of the researcher. Now I have compiled the recent works which have been done on hard sound analysis using signal processing techniques. So the first and foremost step for any hard sound analysis, which is meant for automatic detection of cardiac abnormalities, is segmentation of first and second heart sounds. So whenever we go for any screening system, or whenever we want to design any cardiac screening system, the first step is to segment first and second heart sounds, which are S1 and S2 are the fundamental heart sounds, and these are called the healthy heart sounds of the PCG signal. And so the first step is segmentation, and available hard sound segmentation techniques, which has been reported for the decades, are mainly classified, or mainly they can be broadly put into two categories: those algorithms which are based on electrocardiogram signal as reference, and another segmentation technique which are independent of electrocardiogram signals. So whenever we go for segmentation of S1 and S2 signals, either we go for those algorithms, those segmentation techniques which can detect or which can segment S1 and S2 from phonocardiogram signal, which will be based on electrocardiogram signal, or which will be independent of ECG signal. But when someone goes for the first method, the algorithms which uses electrocardiogram signal or which requires electrocardiogram signal as a reference, in that case, uh, it requires simultaneous recording of electrocardiogram signal also, along with our phonocardiogram signal. And it gives a discomfort to the patient because it requires some circuitry. Though this method is very robust, and it becomes more reliable, it's more accurate, but still researchers do not prefer much the algorithm which requires ECG as a reference for segmentation of heart sounds S1 and S2. So most of the researchers, they follow the former method, the second one, where the segmentation techniques are independent of electrocardiogram signal, which doesn't require electrocardiogram signal as a reference. So only phonocardiogram signal will be sufficient for segmentation and for further processing. So in this context, Liang and his co-researchers, they have presented an envelope envelogram based approach for segmentation of first and second heart sounds, S1 and S2 respectively. So actually, when we hear this first and second heart sounds, love and dove heart sounds, we find that there is certain changes in their frequency components and in their amplitude. So we exploit the energy of S1 and S2 for their location finding, and for their detection. That's why, based on Shannon energy, uh, they try to get the envelope of S1 and S2, and based on the energy they uh, try to segment S1 and S2, as this is the first and foremost step required for any automated heart sound analysis or heart disease diagnosis system. That's why this is the first step. So they have presented a method which is based on the envelope program. Similarly, in one of the recent work, it was reported by Chen and his co-workers, and they have reported a deep neural network approach for segmentation of heart sounds S1 and S2. Like in previous method, they required energy and also the timing information, as we know that systolic time is less as compared to the diastolic time, means the time differences between the occurrence of S1 and S2 is less as compared to between S2 and S1. So so independent of timing and amplitude information, they have used a deep neural network approach for recognition or for detection of S1 and S2 hard sounds. And it was a better approach as compared to the previous one. So then we know that there are some other hard sound components also for in our phonocardiogram signal. Like S3, this may be a normal hard sound in case of a children, kids, or some athletes. But the presence of this third hard sound, this may be a indication of heart abnormalities in case of adult and elderly people. So some of the, and we know that this S3 has low frequency and low amplitude as compared to the first two hertz sounds, S1 and S2. So it becomes a very challenging task to detect third hertz sound. That's why most of the methods which have been reported in the literature for detection of heart sounds, third hertz sounds, are mainly based on the time frequency representations, which uses like WVD, Wegener value distribution, or smooth pseudo Wegener value distributions, and like S transform, STFT. So different kinds of time frequency representation have been used to detect third hertz sounds. Then another components which may be available in hard sounds are murmurs, and these murmurs are mergers. These murmurs mainly these are found between first and second hard sounds. So this will be called systolic murmurs, and if these murmurs are present in between S2 and S1, then it will be diastolic murmur. So whether it's a systolic murmur, diastolic, early diastolic murmur, late systolic murmur. So we have different kinds of heart murmurs, which refers to some abnormalities in the heart. So their classification have also been reported, which uses some of the features, some of the suitable features like spectral features, MFCC features, some energy features, some autocorrelation based features, followed by followed by classification using classifiers like support vector machine. So murmur classifications. So a lot of work has been done for the murmur detection from the phonocardiogram signal also. And then one of the very interesting work related to this heart sound analysis was done in separating heart sounds and lung sounds from the breathing signal. So whenever we take the breathing, so whenever somebody breathe, so when we want to hear that sound, then heart and lung sounds, both sounds are present in that breathing signal. But a cardiologist, he may not be interested in the lung sounds, and this lung sound may interference may it may interfere in the exact diagnosis of the heart sounds analysis. That's why one of the important work where state of art one of the important work in the state of art is separation of heart and lung sounds from the breathing sounds, so that we have two separate heart sounds, two separate sounds, namely heart sounds and lung sounds, and then independent analysis of these separated signals can be done, and it can help in automated screening systems of heart disease or lungs disease. So they are like non-stationary lung sound extraction algorithm was proposed by Mondal and his colleagues, which uses empirical mod decomposition and high pass filtering to separate lung sounds from the recording. And this recording contains breathing sounds where both heart and lung sounds are present. So here they have used, as we know that heart and lung sounds are non-stationary in nature, so they have used non-stationary decomposition methods like empirical mod decomposition, which decomposes a complex non-linear signals into different frequency components or different sub-components, such that when we try to combine all these, it becomes closer to that of the original complex signals. But still, there will be some error in terms of residual or some components will be lost because it's a decomposition technique. Then moving to the research areas. So what are the trending problems available, or what are the research areas, or what problems can be found out in this research topic, hard sound analysis. So we have different kinds of problems available when one goes for hard sound analysis. So in the recent trend, it has been found that there may be various objectives in this research topic, where someone wants to do hard sound analysis using signal processing and machine learning. So one is to develop an automated noise robust framework for identification of S1 and S2. As we know that this identification or segmentation of first and second head sounds is the first and the foremost step required in any automated heart sounds analysis for detection of pathological events. So the first step is to develop a framework that can identify exactly the position of S1 and S2, because once these are identified, S1 and S2, first and second heart sounds, then we can easily go for detection of third hertz sound, fourth hertz sound, and we know that murmurs are present in between S1 and S2, and also between S2 and S1. That's why the correct location of these S1 and S2 are very much required, and this is the first step for any automated hertz sound analysis. And it is a bit easier, I cannot say easier, but at least these first and second hertz sounds are prominent as compared to the third heart sound, fourth heart sounds, and heart murmurs. And another interesting problem area can be like separation of heart and lung sound from the breathing signals. So that once the heart and lung sounds can be separated, one can go independent analysis of heart sound signals for developing some of the automated heart sound analysis framework, and same is true for the independent analysis of lung sounds to in order to detect, in order to screen lung sounds, in order to develop some of the screening systems in for detecting respiratory diseases using lung sound analysis. And 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 we cannot directly go for some application of some filters to separate heart and lung sound from the breathing signals, because majority of the frequency components of heart and lung sounds, they overlap, and this is known as spectral overlapping. So we cannot directly use high pass filter or a low pass filter to separate this. If we go for direct application of heart and direct application of low pass filter or high pass filter, then there will be significant loss of information of one signal from the another. And that's why when we go for separation of heart and lung sounds, generally they follow non-linear decomposition techniques like empirical mode decomposition or ensemble empirical mode decomposition. Then it's improved versions like SIMDAN, residual SIMDAN, enhanced SIMDAN, and then variational mode decomposition, complex variational decomposition, and lot of changes has been taken place. And then another objective in this heart sound analysis may be focused in detection of abnormal heart sounds S3, because in case of elderly people, its presence is related to some cardiac abnormalities. Similarly, S4 detection, and one problem may be to develop an automatic detection framework for pathological heart murmurs, where it will detect heart murmurs. Then one I have not mentioned in this presentation slide, but one maybe in the hardware side, like as we know that like electronic stethoscope, these are very costly equipment. So it cost goes to 60 to 70,000, the electronic stethoscope. So we can go for designing a low cost stethoscope using our PCB, which can be used for the recording of the signals. And my talk uh, or the presentation, I have made this in the two sessions. So I will try to cover at least I will try to cover module 3 in this talk, and tomorrow I will try to cover the module 4 and 5th. So mainly in the first, I will be discussing those tools and techniques which are required for the analysis of these heard sound signals. So it will build our basic mathematical concepts which can be used, which will be required to analyze non-linear and non-stationary signals like heart sound signals, phonocardiogram signals. Then we will see one of the work which has been done for identification of first and second heart sounds using some features, mainly spectral and convex hull features. And then we will also see how to characterize heart sounds using deep learning methods. And then in tomorrow's talk, I will cover the detection of third heart sounds using a nonlinear decomposition technique, namely variational mod decomposition. Then followed by like detection of heart murmurs for balanced as well as unbalanced data set. And then conclusion will be given at the end. So let me start with giving very briefly, about some of the signal processing tools and techniques that will be required for analysis of non-linear and non-stationary signals like phonocardiogram signal. And these techniques, you will find that these techniques are also applicable for another non-linear and non-stationary signals like our speech signals, electroencephalogram signals, and other biomedical signals. So it's very preliminary. So let me just tell about some, very briefly I will go because I have to cover some other topics also. So I will give a very basic about some of the non-linear decomposition techniques. As I told you, there are techniques which shows some frequency uh, uh, overlapping, that is called spectrum overlapping. For example, if I consider breathing sounds, then there is a heart sounds also and lung sounds also, and we cannot separate directly using a low pass filter with given cutoff frequency or a high pass filter with a given cutoff frequency, because this there are some spectral overlapping between these signals. So the best way is to decompose these non-linear and non-stationary signals using some of the non-linear decomposition techniques like empirical mod decomposition, ensemble empirical mod decomposition and its variants, and 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 then followed by or and a newer method, or a better approach as compared to as compared to empirical mod decomposition is our variational mod decomposition, as it is more robust to the noise and it has certain advantages over ensemble mode decomposition. So when we talk of variational mode decomposition, so basically it's a non-linear decomposition techniques that decomposes a complex non-linear non-stationary signal into a discrete number of subsignals or modes, and these modes, their frequency will vary, or in other words, they will be fast moving comparatively, they will be slow moving, so their frequency components will vary. I mean that if we have a very complex signal, so if it is fed to a black box which uses variational mode decomposition, so it will decompose that signal into a discrete number of subsignals in such a way that if we combine all these subsignals, it should be close to that of our complex signal, but definitely there will be some differences as it is based on on optimization techniques. So I'm not going much detail in mathematics, but just to give a basic idea that what is variational mode decomposition. So basically, it decomposes a signal into different number of sub signals. The sparsity prior to each mode is chosen to be its bandwidth in spectral domain. Means how it decomposes the signal. So basically, it's an optimization process. So first, it takes the central frequency, so that whole complex signal. How means actually the user gives that in how many number of modes they want to decompose that signal, and based on that number of modes as an input, it tries to optimize the it does optimization, and it try to assign some of the central frequency, and then it assigns the bandwidth so that it decomposes the signal into different bandwidth. And this scheme to access the bandwidth of a single mode. Suppose we want to decompose a signal into n number of modes. So what should be the mode of a single mode? So that is governed by optimization technique, and they first make the signal analytical using Hilbert transform. Then the frequency spectrum of each mode is shifted to the baseband. Because once it is shifted to the baseband, then we can go for Gaussian smoothness. So this is basically, it's a constraint variational problem. Why it is a constant? Because actually when we have a complex signal, say we have a complex signal, this f is a complex signal, say it's our hard sound signal, it's a segment of our hard sound signal. So when VMD is applied, basically this variational problem is expressed in such a way that it tries to minimize using optimization technique. It tries to give central frequency and bandwidth for each mode in such a way that that sum of all the different modes will be equal to that of the complex signal. So they try to minimize this. And here, if we see the mathematics here, then basically we are doing the Hilbert transform. So here we are doing the Hilbert transform, and then we are shifting it so that it can be a baseband. So this is actually shifting process e to the power minus j omega k, and then we are trying to minimize. So we are taking here um, norm of this function so that this error can be minimized, and our sum of all these decomposed modes should be close to the complex signal. So basically, variational mode decomposition, it decomposes a complex signal into different number of modes. And then a very good concept which is often seen for analysis of hard sound signals is actually when is analytical signal representation of narrow band limited components. So whenever we apply variational mode decomposition, these different modes are known as narrow band limited components, because its bandwidth will be low as compared to the complex one, as it is the decomposed ones, or these are the different modes. So for analytical representation, mainly the advantage is that we find the magnitude and phase. That's why we go for analytical signal representation. And then one of the very important parameter for a non-stationary signals, like our amplitude, like our non-stationary signal, say our phonocardiogram signal, is the amplitude modulated bandwidths. So here, like when we just say bandwidth of a signal, so it doesn't contain any information regarding the exact reason for the presence of range of frequencies, that whether the range of frequencies or the bandwidth which we have has resulted from variation in amplitude of the signal alone, or deviation in average frequency, or due to combined effect of both the variations of amplitude and frequency. So when I say bandwidth of a speech signal is say 3.3 kilohertz, so I cannot say that this bandwidth has resulted from the variation of frequencies of the speech signal or amplitude. That's why we always go for amplitude modulated bandwidths and frequency modulated bandwidths. So earlier we have the concept of only bandwidth, but here for non-stationary signal we go for amplitude modulated bandwidth. So what is the amplitude modulated bandwidth? What is the frequency modulated bandwidth? Because this may be a very suitable feature for the classification of normal and abnormal heart sounds. So how to calculate amplitude modulated bandwidth of a non-stationary signal? So first we decompose that signal using VMD, and then we use the, like once we have, like for any analytical narrow band component signal Z of t. Say it is one mode. It is the one mode which have arised from VMD. So we can get the central frequency using this term, where Fourier Z of omega is the Fourier transform, E is the energy, and then we can calculate the bandwidth using this formula. So 1 by E integral of dA by dt whole square dt. So it's a amplitude modulated bandwidth. Similarly, we can calculate the frequency modulated bandwidth, and combined bandwidth also can be calculated using this formula. So these are very important in order to characterize hertz sounds. Now we have some good parameter which can represent analytical signals or non-stationary signals. So this is convex hull. So convex hull. So in the Euclidean space, this convex hull, it defines the smallest convex polygon enclosing set with its point lying within a polygon or on its periphery. So basically, it's define the a region. Say if we are considering uh, electrocardiogram signal, or if we are considering phonocardiogram signal. So if you want to segment certain region, then definitely their areas will be different, as they occurs for different duration. They have different energy levels. So these features are very helpful. And then based on this, we calculate the area. So convex hull area. So convex hull area, basically it signifies the total spread of the region of interest. Uh, and it also signifies non-linearity strength. Like if the convex hull area is more, then we say that there is a more non-linearity strength present in that. So it may happen that for segmentation of S1 and S2, this parameter may be different. So it will be a suitable feature for the identification or for classification of the different components of a phonocardiogram signal. And we get the area using this formula. So and let me switch over to one of the recent work reported for identification of first and second hertz sounds using these features. These are called spectral features. So identification of first and second hertz sounds using spectral and convex hull feature. So we will see what is the pipeline, or what is the general what techniques can be used to to exactly identify first and second hertz sounds. So here this is the proposed flow diagram for S1 and S2 classification. So here, like, we have the PCG signal here, phonocardiogram signal. So this raw phonocardiogram signal. So we have here cardiologist or physician helps to segment that region. So we make a training database by segmenting S1 and S2 manually by the help of physicians. And then these manually segmented S1 and S2 signals, like this is S1 and S2. So each S1 and S2 signals is fed to VMD block here. So this variational mode decomposition, it decomposes the signals into different modes here. So we have kept the minimum number of modes here, that is 2. So either S1 or S2, when it is fed to variational mode decomposition, it decomposes the signals into 2 modes. And then from each modes, we extract spectral and analytical feature. And then it is then a super vector is formed by cascading all these spectral and analytical features, and it is fed to SBM classified to see the output, whether it correctly recognizes S1 and S2 or not. So this was for the training phase. We will train this classifier based on the fact that we will give the correct database with the help of physicians. Then in the next, again, a recording of PCG signal will be given. And here, now, unlike in case of earlier, we have taken the help of a physician. Now, as it is automated system, so we will use hard sound segmentation unit, which uses Shannon's energy to segment S1 and S2. And then the segmented S1 and S2. So S1 again it will be decomposed into two modes using variational mode decomposition, and the features will be extracted from both the modes, and then again it will be fed for a classifier. So this is the proposed flow diagram for identification of S1 and S2. Means first the recording of heard sound signal will be given, and then from there heard sounds of S1 and S2 will be segmented without help of any physicians. Then segmented region of S1 and S2 will be decomposed into two parts or two modes, and features will be extracted. It will be after extraction of feature, it will be fed to a classifier. And then, like when we talk of feature extraction, then feature extraction we have used here spectral and analytical feature. So in case of spectral features, we can see here like here we have segmented S1 and S2, and NBCs means it's modes. Like if we have a S1, it has two modes, mode 1 and mode 2. If we have a S2, it is decomposed into two modes. So NBC1, NBC2, narrow band component 1, narrow band component 2. I mean S1 and its two modes, S2 and its two mode. So if I am talking of S1 original S1 signal and its two corresponding modes. So we take spectral features. So we calculate amplitude modulated bandwidth because frequency modulated bandwidth doesn't contribute much. We have seen this. And then we calculate the area, analytical feature in terms of convex hull area. So we have used two features only, amplitude modulated bandwidth and convex hull area. So these two features can also be applied for another signal if it becomes suitable in classification. So we make here a feature vector, and then this feature vector is fed to SBM classifier. So for any non-stationary signal, these features may be good. So initially, so here I have whatever I have discussed, it is written here. So this is the block diagram for identification of S1 and S2. Then mainly we have considered online data. So like online data are publicly available. It's freely available in Littman, Michigan Heart Sound Database, Washington Murmur Library, and we have considered a total of 351 S1 and S2 samples. And the corresponding sampling frequency of the heart sources were around was 11,025 11,025 hertz and 41.4 kilohertz. And then we have, by our own electronic stethoscope, we have recorded the data of 8 subjects whose sampling frequency were 44.1 kilohertz, and total of 60 S1 and S2 samples each we considered. And for pre-processing, we used a cutoff frequency of 400 hertz because most of the energies of first and second hertz sounds lies below 400 hertz. That's why. And for feature extraction, we have decomposed this pre-processed S1 and S2 components into only two number of modes, and we have extracted spectral features, that is amplitude modulated bandwidth and analytical features in terms of convex hull area, and we form a feature vector, and when we put to the so we have put that into the conventional classifiers as well as to the deep belief network also, and we found the results. Results that these features it becomes very significant. They are very relevant. They have proved themselves very relevant in classification of S1 and S2 to a very high classification accuracy. So here just I have taken the waveform plot and spectrogram of S1 and S2 here. So this NA is the normalized amplitude. So this one is S1 signal. This is S2. So we can say that systolic time period is less as compared to the diastolic time period, which is between S2 and S1. S1, S2, sorry, S1, S2, S1, S2, S1, S2, love, dub, like this. And this is the spectrogram, which says that most of the energies are concentrated within a very low frequency here. So here it is 1 kilohertz, so less than zero point 0.5 kilohertz. That's why we justify the use of 400 hertz uh, for the cutoff frequency of low pass filter. And then this is S1 signal, and it is decomposed into two modes using variational mode decomposition. So first mode is slow varying mode, and the second one is fast moving mode. Similarly, this is S2 signal, and these are the corresponding modes here. And so modes, and then we have calculated here. It's a basically an analytical signal representation where we have phase and magnitude. So if it is like here, so this is S1 and it's two modes. Similarly, this is the analytical signal representation of S2 and its two modes here. And we find that for if like signals are more concentrated here as compared to this portion, so we say that it has more non-linearity strength in this. Similarly, so when we come to the summary of this work, then we find that classification performance on both the online and experimental data set based on the proposed features, that is amplitude modulated bandwidth and convex hull area, that is spectral and analytical feature for 5 different cases. Means we considered only signal, then only one mode, then second mode, then combined mode, then signal with both the modes. So we have considered all, and we find that in most of the cases, the achieved accuracy is higher when the signal and both the combined modes are considered. The reason is it gets good features when it uses signal as well as both the modes, so that they increases the dimension of the final vector before feeding to the SPM. So it gets sufficient information to exactly classify between S1 and S2. And we have found that SPM achieves a classification accuracy of 99.49 for the online dataset, and for and it is for 100 runs, and KNN it achieves high accuracy of 99.62 for our experimental data or for our recorded data. And and we have compared this with the previous work, which have been classified based on the MFCC feature, Males frequency substrate coefficient features and its derivative features, and this performance it deteriorates. The performance which have been previously reported is less as compared to the features which we are using in terms of spectral and analytical. So this method is superior as compared to the state of art method. And then male frequency substrate coefficient, these uh, it significantly suffers from the noise, whereas spectral features and convex hull area, this doesn't much affected by the noise. So in case of noise also, this proposed method, which uses amplitude modulated bandwidth and convex area, its performance is good as compared to the state of art which uses MFCC features. So it will be of great interest to study the proposed methodology in context of segmentation of other biomedical signals like electrocardiogram, electroencephalogram, or electromyogram, as all are non-stationary and non-linear signals. But certainly, it's not that it will be it's a universal feature and it will be fit, but it would be of great interest to study these features in different bioorigin signals like electroencephalogram or electrocardiogram signals. So let me see the time now. It's 4:15 already. So I feel, let me ask Swanirbar sir.
Hello.
So yeah, sir, I think I have taken a bit more time, so I'm really sorry.
No, actually, you started late. The students were joining in late, so you started already in 3:15 or so.
Yeah, yeah,
So
yeah.
the same. You have taken exact 1 hour only, but the issue is that we had very few participants at uh, three. So you will be continuing the next module, I guess, in the second phase.
Yes, sir. As you wish. Yeah. Tomorrow also I can present. As per
And
your time. Yeah.
now, if the students are having any question, kindly let us
Yeah.
know.
Yeah. Yeah. The questions are most welcome.
If you are having any questions. So in case they have no question, say, or even if they have some question, they can take it up tomorrow also, because you will be continuing with this thing. So thank you very much for being here, and I had requested you to fill up for one of our teachers slot. Thank you. Uh, I hope say the participants have gained a lot of things from here, because IT, CS, EC, they are all working in signal processing areas, either in this form or the other form. So thank you very much
Uh,
for being here. We'll
Yeah.
meet again tomorrow.
yes, sir.
So thank
So
you.
yeah.
So
So before I leave, just uh, I would like to convey my sincere thanks to all of you, the participants, for your patience, listening, and valuable time. And once again, I would like to show my gratitude to the coordinator, especially Swanirbar sir, head of the uh, Department of IT, Tripura University, all the organizing members, for giving me this opportunity to present my research work. So I am really privileged and grateful to you all, and I look forward to see you tomorrow also. So thank you very much, and with your permission, I would like to leave the session now.
thank you.
Yeah,
Thank you.
Yeah.
thank you.